everybody. I'm standing up.
Hi everyone, it's a pleasure to be here. I will talk about stellar spin and exoplanets today. And let's start with this. Why do we actually care about stellar spin? There are quite a number of reasons why we as exoplanet people... Oh, thank you. Am I loud enough or would you like me to wear this? It's fine. I'm loud. Okay. Ah, that's why we know. Okay, I can do that. Okay. For the tape. Okay, let's see. Okay, how's this? Woo, good. So why do we care about how stars spin? This here, what is here, is a picture of our own sun in soft X-rays. And one of the amazing things here is that the outer solar atmosphere shows very interesting magnetic phenomena. And these are all driven by the spin, by the rotation of the sun. So basically we have differential rotation on the surface of the sun and also radially throughout the sun, and this drives the magnetic dynamo. So basically the rotational energy of the sun is transformed into a very highly structured and time variable magnetic field, and this produces very interesting observable phenomena. So we have the pure existence of the magnetic field, which comes from the rotation. We have what we can see here. We have these solar flares, which are basically rearrangements of the magnetic field lines that release energy. And we see these sudden heating events in the solar or in the stellar atmosphere. And we see this brightening in various wavelengths that we call flares. Associated with that are coronal mass ejections. And of course, the very existence of X-ray and UV emission from these sort of intermediate or also low mass stars is driven by the magnetic field and therefore ultimately by the stellar rotation. So we care what the star does with its rotation over time. Now, we know that a lot of stars have exoplanets. And some of them even have very massive and very close-in exoplanets that we call hot Jupiters. This here is one of those systems, the system WASP-12, drawn to scale. So we have here a solar mass, roughly solar mass star. And we see here the exoplanet. This is actually drawn to scale. You can see that this hot Jupiter orbits the host star within very few stellar radii. And if I overplotted the solar corona here, you could actually see that this is basically within the extended streamers from a corona here. So with these closed systems, we expect some sort of interaction taking place between the two components. We can think of this like a binary star system with very different masses. And what sort of interaction can we expect? Of course, gravitationally, we can expect some tidal interaction between the two bodies. What we can also expect are magnetic interactions, because we know that both stars and planets have magnetic fields, so there will be something going on there. And finally, and this is also a very active field of study, we have some influence on the planetary atmospheres if they are that close to the host star, because they are very strongly irradiated, they are heated, they are embedded in the stellar wind that flows out from the star, so there's lots of interesting effects going on. What I will focus on today is the tidal interaction between a star and its massive close-in planet. So what does this look like? This is our star, and typically when we have a middle-aged star like the Sun, it's rotating fairly slowly. We have a rotation period for the Sun of about 30 days. With these hot Jupiters that are orbiting the stars, the orbital periods are much shorter than that, a few days, 2 days, 3 days, 4 days, something like that. So what is happening in such a system is that we have a slowly rotating star here, a quickly orbiting planet, and what happens here is that the planet raises tidal bulges on the star. And conversely, the star also raises tidal bulges on the planet, but we won't care about that for now. What you can see here are the tidal bulges, and since the star is rotating more slowly than the planet moves on its orbit, the tidal bulge is lagging behind the planet. So this stuff is happening in this plane here. And what that means is we have an induced tidal torque, because basically the planet pulls on this tidal bulge here. And what that induces is a transfer of angular momentum from the planetary orbit into the stellar spin of the host star. Actually, we know that this stuff is happening from our own solar system. For example, for the Earth-Moon system, we have the reverse effect. So the Moon moves outward slowly over time, because the Earth is the fast-spinning body here in the system. Oh, and of course, when this is happening, this of course means that then the planet spirals in slowly over time as the star is spun up. Now, if we want to test for such an effect observationally and see how fast this is happening, if this actually influences stellar rotation and spin on a measurable level, how do we do that? The thing is, the stellar spin, as we know from the Sun and other stars that we observe, doesn't stay constant over time. It changes by itself. And this is because we have magnetic braking. So all cool stars, and also hot stars actually, shed an ionized stellar wind. And this wind couples to the magnetic field lines, as you can see here nicely. So since it is emitted, it basically loses angular momentum due to that process already. So what we have for all these cool stars is they start out as young, fairly active, quickly rotating stars. We see here lots of star spots in my little cartoon here to indicate the activity of these stars. And over time, they become slowly rotating and inactive. So basically, we want to do a fairly simple comparison. What you see here is stellar age on the x-axis, and on the y-axis you see one measure of stellar activity, in this case X-ray luminosity. You see stars of different masses here with the different colors, but basically what we see is that at young ages of the star we have these highly active stars, and as they spin down they lose their activity. And in principle what we want to do is fairly easy. We want to say we have the star with a hot Jupiter, and we say, okay, it has this age here, and then we compare if it is overactive to what we expect or if it's not. Would be a fairly easy measurement if we didn't have this problem that we generally don't know how old a typical field star with an exoplanet is. This is actually a very hard problem. We don't know where to put our typical field stars on this x-axis, how to do this comparison. So the question is, how can we solve this problem? What we can do is we can look at certain systems that allow us to do an age comparison. What I have here are X-ray images of systems that have two stars. It's a wide binary system, and one of the stars has a known exoplanet. And what happens in these systems is that we have two stars of the same age, and if we have a hot Jupiter in one of those systems, we expect that that star will be rotationally influenced over time, and the other star won't be. So this other star serves as a negative control here. And so far, I've collected 9 X-ray observations of such systems. There are 10 more coming up over the next few months. And as you can see, usually both A and B components, both stars are detected in almost all the cases. And now we can compare what the activity levels of these two stars are and what we see there. So in this sample, we have a couple of systems where we expect strong tidal interaction between exoplanet and host star. So we have a fairly low mass star with a thick convection zone, and we have fairly massive close-in exoplanets. In other cases, we have either a very high mass star, or we have a really, really tiny exoplanet where we don't expect much to happen in terms of tides, right? So this is, drawn to scale, the tiny, tiny exoplanet. So there's not much going on here, hopefully. And we will see what the observations say about that. So how do we compare this? Here's again the big plot, how activity evolves over time. And now, for one of the systems in which we expect a weak tidal interaction to happen, yes, we look at the secondary star in the system, the one without a known planet, and we measure its activity level. It's fairly low. We assume this must be a system with a very old age here. Now we look at the planet-hosting star in the system, and if there's really only weak tidal interaction going on, it should be somewhere here with its activity level. In this specific system, the star with the planet is a bit more massive, so we expect it to fall somewhere here on the blue track, but it shouldn't be much higher than that. And indeed, what we find is roughly what we expect in the system for weak tidal interaction. Both stars show an activity level that is appropriate for their common age. Now, what happens when you go to one of the more interesting cases? Two of those cases I've shown here. So these are, again, the stars in the system that don't have known planets. And here we see, again, that the activity level is fairly low. Again, these must be systems that have a fairly old age. Now, in these cases, again, the stars that host the planets are a bit more massive, so they should fall somewhere here. But when we measure their X-ray luminosity, we actually find that they happen to be here. So in this case, it's almost an order of magnitude higher than we'd expect. And in this case, for Corot 2, it's even 2 orders of magnitude more active than we would expect from the other star in the system that has the same age. Now, how does this look for the whole sample observed so far? We have here all the 9 systems. And what you see on this plot are, as the red dots, the stars that don't have any known planets and their activity level. And now, to make an estimate for the other star in the system, we have again to correct a little bit for stellar mass differences. And those are the light blue boxes. This is our expectation for those stars. And in the regime where we only expect weak tidal interaction to happen between star and planet, the actual measurements of those stars, the blue diamonds, fall basically very close to what we expect to see for them. But in the cases where we expect to see strong tidal interaction, we find consistently, even though this is a small sample size, we find consistently that the hot Jupiter hosting stars here are much more active than they should be when we compare them to their same age stellar companions. So this is a very interesting thing. And what can we say so far, halfway through the observational program, is that we actually do see some planet-induced enhanced activity effects here. What we need for those to actually see them in those two samples is we need a very massive exoplanet, so at least a Jupiter mass. It has to be in a very close orbit. The whole star shouldn't be too massive because then it just gets a bit tricky to whip that whole thing around. And what we see are activity enhancements of 1 to 2 orders of magnitude. I'm personally very excited to see what the other half of the sample will bring. And with that, I'm happy to take questions.
Katja, I would expect a stronger effect for stars with a thinner convection zone than the thicker one. Am I right?
No, actually, so we expect to see a stronger effect if the whole star is less massive. So basically, if you go to a K or M-type star that has a thick convective zone, we actually expect to see a stronger effect. This is based both on the mass ratio between the exoplanet and the star. And there are some tidal theories. This is always a bit tricky because the tidal theories, it depends on whom you ask. But generally, people expect that when you have a thick convection zone and you induce that tidal bulge, that there's sort of more tidal lag in those systems than the ones where you only have an outer radiative zone.
So it suggests that the effect is stronger by the angular momentum transfer, not effect on the magnetic field in the region.
Well, this is the thing that I test with my observations, right? I'm testing for the tidal part. If you actually followed exoplanets around for full orbits, maybe you might trace some magnetic effects as well, but the observations as I do them here aren't really sensitive to the magnetic part of it.
So, what is the expected lifetime of those systems for absorption?
So that is a very tough to answer question at the moment because we don't know these tidal quality factors of the stars very well. So what people have done in recent years is population studies to look at how consistent is the number of hot Jupiters we see right now with certain tidal info models, right? And there are some constraints on the lifetimes of these systems, but it's not very well constrained yet. What we're actually observationally looking for, and this would be a smoking gun for this, if we actually had a transiting planet and we observe it over, say, 20, 30 years, and we actually see the orbital period getting shorter. We try to do this for HD 189733 because this is the oldest known transiting planet, but so far, I mean, it's a tiny signal we're trying to measure.
So do you have any means of measuring the rotation rate of the stars in question?
Actually, in these cases here that I've shown, I haven't shown it on the plot, but yeah, in those cases we actually know the rotation periods, and they are actually also rotating faster than they should be for the system age. So it's not only the activity that is higher, it is the actual rotation period that is faster than we would expect.
So I think we do have to move on. So next speaker is speak on magnetized gas clouds can survive acceleration by Poppenhager.
Great. Well, it's a pleasure to be back here for Meredith and I's 5th reunion. So I'm going to talk about magnetized gas clouds can survive acceleration by hot wind. And what you can see here is just kind of a nice image of the Kelvin-Helmholtz instability in two fluids which are shearing against each other. We're all very familiar with this every morning when we put milk in our coffee. And this is work I did while I was at Berkeley, but is still ongoing now that I'm in Boulder with Mike McCourt, who used to be here, Anne Marie Madigan, and Elliot Quadert. So the underlying motivation for this is that dense cold gas clouds interacting with the hot wind is kind of a ubiquitous phenomenon in galaxies. So the example that kind of got me really excited about this were gas clouds in the galactic center. So I think you've heard a number of times about the gas cloud G2, which is orbiting closer and closer and now past pericenter with the supermassive black hole. And one conundrum is, why is it not mixing into the hot material around it? It's still a gas cloud as opposed to just totally destroyed. A stronger example might be actually cold gas clumps in galactic winds. So there's a beautiful picture of a nearby galaxy where you have these very fast-moving, strong, hot winds, and you find molecular gas in these winds co-moving with the hot gas. And then another example might be infalling high-velocity gas clouds in our own Milky Way halo. And the expectation through pure hydrodynamics is that these gas clouds should mix in with the hot medium through just the Kelvin-Helmholtz instability. So I'll show a few little simple simulations, but to give you an idea, so here we have a gas cloud with a wind coming in from the left, going past the gas cloud. We start with spherical cloud with the radius r cloud, and basically one of the free parameters is the density contrast between the cloud and the wind. In all of the examples I mentioned before, the typical density contrast, if you assume pressure equilibrium, is about 1,000. Most of the simulations I show are less than that because they're easier to run. And so that's some progress we're still making. And so what's important is the physical timescales. So why do we expect these clouds to mix before being dragged in with the cloud? And it's just a question of timescales. So the classic case is the cloud crushing timescale. So if you look, we'll see again, there's a shock that propagates through the cloud. The timescale it takes to cross the cloud depends on the density ratio of the clouds to the 1/2 power times just the characteristic timescale, r cloud over v flow. The Kelvin-Helmholtz instability, this is the timescale for the instability to develop on the surface of the cloud, has the exact same scaling relation. And so both of these two things, if you have very strong shocks, will eventually lead to the demise of the cloud. And then finally, we have the drag, which goes like the cloud to the wind ratio to the first power. And so you see the drag timescale typically, when this is a factor of 1,000, is 30 times longer than the Kelvin-Helmholtz instability or the cloud crushing time. And so you expect that your coffee and milk to mix completely. So we can actually look here. This is actually at 0.7 times the cloud crushing timescale, and you can see that the cloud is actually changing shape. But here you can actually see that shock propagating backwards through the cloud, and you can start to see the development of these Kelvin-Helmholtz instabilities causing mixing. But we can see this as a movie, just for fun. That in the end, so what we're seeing is actually a projection of the die of the cloud going through the cloud and actually asking, what does it look like as it mixes? And you can see basically, oops, I was trying to pause it, but that's not working. The cloud becomes kind of a pancake and then just very quickly mixes in. And this almost always happens by 10 cloud crushing timescales or 10 Kelvin-Helmholtz instability timescales. And the problem arises that if you look at the magnetized gas cloud in the galactic center, oh, I cheated, or the gas clouds in galaxy halos, the drag timescale is always much longer than the lifetime was required to get the cloud to those radii. On the other hand, the Kelvin-Helmholtz timescale is always much shorter than the timescale it took to get there. So in any good astronomy talk, the next question should be, what about magnetic fields? And so the magnetic fields suppress the Kelvin-Helmholtz instability. This is a result that's been known for a very long time. And so you might expect, you can kind of contain a gas cloud through just magnetic fields alone. They also supply pressure and tension. So a cloud that might want to compress because of the ram pressure in front of it. The magnetic fields can provide some pressure and actually keep them together, but they can provide tension and keep it fixed together. But there's this other problem, which is the magnetic Rayleigh-Taylor instability can disrupt the clouds themselves. And so what this is, our first simulations were like a knife going through butter. If you have magnetic field lines, they can get caught in the front of the cloud, and you eventually just get a ton of magnetic pressure there, which can just eventually cut right through the cloud. And so here's kind of a physical example of that. So here were some simulations that have been done in the past, looking at exactly this case. You have a gas cloud with a vertical field in the cloud and outside the cloud. And then as time goes on, you see that you get this kind of vertical field lines just getting caught right in the front. And if you continue the simulation on, you find that it eventually just cuts right through the cloud and they mix fairly thoroughly. And the Rayleigh-Taylor stability, like everything else, has the exact same scaling relationship. Goes like the density ratio to the 1/2 power. So we're not saved quite yet, right? The And this is for when the magnetic pressure and the thermal pressure are about the same. So we're not saved because the Rayleigh-Taylor instability you might expect to disrupt clouds. And in fact, the previous papers pointed out that actually when you have strong magnetic fields, the cloud disrupts even faster than the Kelvin-Helmholtz instability would suggest. So we thought, well, vertical fields might not be what we should expect in gas clouds. We might expect the gas cloud to perhaps be isolated magnetically from the rest of it. If you have a turbulent magnetic, turbulent structure, you might expect a turbulent field inside of it. Unfortunately, there's no such thing as a force-free field of an isolated gas cloud. So we do something called the truncated force-free field. So basically, we set up our initial conditions so that the magnetic fields are all tangled, but they don't want to just spread apart right away. They still do, but that's the best we can do. And then coming in is a vertical field here. And the key thing is that one, we initialize our conditions such that these fields do not actually intersect with each other. So there's very little overlap between the magnetic fields. And we basically follow the same type of parameters. We have a wind speed. In all of these systems, you kind of expect the cloud to be moving at near the virial velocity. So the sound speed and the wind speed are of order 1. So here is kind of an image showing the final result of our first paper on this. On the left, we have MHD simulations. Again, these are basically projections through a die in the gas cloud. And on the right are the hydro simulations. And the top is at the 5-time TCC, the cloud crushing timescales. You see it's not quite completely disrupted in the hydrodynamic case. And this is basically when they're co-moving together. And the first thing you notice is, I should also point out that we're looking at 2 different orientations. The wind's always going this way, but sometimes we're looking down the magnetic field lines, and sometimes we're looking across the magnetic field lines. So here's when we're looking down the magnetic field, and this is when the outside magnetic field is vertical here. And here it's through the board. And you see, one, that you don't get the same answer in both directions. So the incoming magnetic field actually leads to disruption. But 2, you don't get complete mixing. So you get these magnetic Rayleigh-Taylor instabilities still. But it doesn't lead to the mixing of the cloud completely. You get a bunch of clumps. And so in this case, it was a density ratio of 50, and we got maybe 10 massive clumps. We're still working on, and I can show you a movie if I have an extra minute at the end, of as we increase the density ratio, what do we expect? And the answer is that as you increase the density ratio, the drag on the cloud becomes larger. You still get only hundreds, maybe 1,000 clumps. What you don't get are billions of clumps. Here's another way of quantifying how clumpy the gas cloud is by looking at the average density squared of the cloud divided by the average density. Well, the square average of the square density divided by the average density squared, the clumping factor. Dashed line is hydro. You get complete mixing, so this approaches unity. And in the case of magnetic fields, depending on the magnetic field of the cloud, 10 is a weaker field inside the cloud. You see that you basically, there's a very big difference between these 2 estimates. So I'll give you some conclusions, and if the alarm doesn't go off, I'll show you one more movie. Magnetic fields suppress the mixing of cold clouds into hot winds, but it doesn't prevent the disruption of the cloud. It goes into fragments and eventually co-moves. That is, the cloud's fragments into maybe tens to hundreds of clumps that are co-moving with the hot wind. And strong magnetic fields in the wind enhance the drag. So I didn't demonstrate this, but as we increase the magnetic field in the wind in front of the cloud, if we make it 10 times stronger, the drag actually can become 10 times larger once the magnetic fields are dominant over the thermal pressure. The magnetic energy density is larger. And since the bell has not gone off, I'll just show when we go to higher densities, we can't actually capture the entire fragmentation and disruption of the cloud. We can only capture the front of the cloud, basically. And so this is a density of 1,000. And in all these cases, there's no cooling. So there's nothing that is allowing the gas to cool, which we might expect in a real physical case. But you can see this is kind of just a low-resolution test that we're still progressing on. But you continuously get lots of magnetic Rayleigh-Taylor instabilities that fragment. But you still don't get billions of cloudlets, and who knows what that looks like. Thank you.
So this force-free model, as you said, you don't have an isolated force-free system. You truncated it. What does it mean? Are there field lines sticking out?
Yeah. So I should have been clear. So we truncated it such that no field lines go out of the cloud initially. Okay. So actually, there's like a 1% level, basically, that you can think the field lines are like at 1 degree from perpendicular. So the clouds, so it isn't completely isolated because we still have a field around it, but it's very close to being isolated. So it's truncated, by basically forcing the fields to be perpendicular to the surface
And
at
this
the cloud
is
radius.
an analytic with spherical harmonic solution, or this
It-
is some randomly generated thing?
It's done, so the solution is done in Fourier space, but in a planar Fourier space, and then we just use the vector potential and just truncate it and calculate it that way. The result is it's not force-free. I didn't show if I let it run, the cloud, you can watch it unwind. And in some of these simulations, as it unwinds, the cloud actually changes shape and gets lift, and it'll start rising in the simulation as it unwinds. So, so the true solution would be you would have some magnetic field that's internally generated. It's a turbulent cloud going through this. That requires just enormous resolution.
So the cloud is certainly turbulent, but also there's no reason to expect the media that it's plowing into also not be turbulent. So did you play around with the initial conditions for the magnetic field, or you just kept it as a vertical field?
So far, we've kept it as a vertical field. There is one reason. So in the case of like G2 in the galactic center, and in other cases, you can ask if you have field lines, how long does it take those field lines to disentangle and become vertical? And in the case of the galactic center, it's much shorter than the dynamical times of our simulation. So there's a good reason. The cloud's very small. Kind of the convective scales we think might be large. Well, we actually don't know. So it's a good question. But I think that physically, the idea that the field outside the cloud should be relatively straight compared to the cloud seems realistic, but it's also really hard to make a turbulent field in front of the cloud, because then we need to resolve all that region so that we don't have any numerical errors.
So now that G2 has passed
Mhm.
the very center, what does your model say about that, or what does G2 tell you about your model?
Yeah, so there's another part. One is including cooling. The other part is including the tidal effect. So I'm pretty sure, except for some very local simulations that like Ramesh and his group has done, the simulations of like the global simulations of G2 have always been hydrodynamic only. And so we're still not in the case of fully MHD G2 simulations with the black hole and tides and everything. But the expectation is that the cloud should fragment. And
It's not doing that.
it's not doing this. No,
They
and
would have seen it. Probably the observations would have shown us. It's doing
well, so this is the interesting question, is that in the beginning, what you get are, when it's completely disrupted like this, it doesn't look like that at all. In the beginning, you get cloudlets that fragment, and we're not including cooling still. And so the fragmentation, I remember asking, Reinhard Genzel's group about the fragmentation. They claim, and other groups don't see, other structures behind the cloud. And so there's a question, and that might be something that could be observable, whether or not the clouds actually fragment or not. So that would be the expectation, is that you would get some fragmentation before you get kind of crazy, swirly psychedelic plots.
I'll take one more briefly.
Is there any hope of measuring any of these magnetic fields or finding evidence for it?
Yeah, so in the case of G2, it's not exactly there, but there's a magnetar that was discovered near G2. And so from the rotation measure of the magnetar, they can actually infer the line of sight average of the magnetic field where the magnetar is located. It's farther away from the black hole. But you do get an idea of whether or not beta, so you can't necessarily measure it where G2 is, but you can get an idea of whether or not beta is of order 1 or much less than 1, so much stronger than the thermal pressure, or much less than, or much more than 1. And the answer in that case was that it was very close to equipartition, but there's still some uncertainties in that. But the fragmentation would be a good case. So if the magnetic, to get to the point where you get kind of recover the hydrodynamic solution, the magnetic field outside the cloud, beta, has to be like 10 to the 4 or larger. So it has to be fairly weak fields where you can recover the hydrodynamic solution.
Thank you.
Thank you. One quick thing here, because that's really close to falling off.
Meredith is getting the speaking to us now on measuring the vertical structure of 3 disks with ALMA to weigh planetary systems.
Okay, So as I was trying to decide what I was going to talk about at ITC lunch today, it was actually kind of hard because I'm giving the colloquium this afternoon, so I'm talking about a lot of stuff then. And I just talked at an ITC lunch about 6 months ago, so you guys have heard everything or will hear everything that I have to talk about, except I was saved because I got a new delivery of ALMA data about a week and a half ago. And so what I thought I would show you today is what's in some ways sort of a half-baked project. I wanted to show you my hot-off-the-press ALMA data and tell you why it's really exciting, and tell you what the preliminary results from examining the data from the telescope are. But I also thought it would be fun because it's a project that I've been thinking about for a really long time. In fact, it's the idea for the project I came up with. As Ryan said, we defended our PhDs here about 5.5 years ago, and it's something that I came up with in my last year of grad school and have been working on since then. So it's actually really nice to kind of come full circle and be able to show you the results of this idea that was planted while I was still a PhD student here. So the picture here is a debris disk called AU microscopiae, AU MIC for short. And what I'm going to be telling you about today are why we should image it with ALMA, why it's very exciting to image it with ALMA, and then at the end I'll show you our ALMA data that we just got very recently. So just to make sure everybody's on the same page about kind of what we're talking about evolutionarily, when we talk about circumstellar disk evolution, these are disks of gas and dust around young stars, and there are sort of two endpoints of evolution. On the one hand, we have protoplanetary disks, which are found around pre-main sequence stars. These disks are very, very gas-rich. About 99% of their mass is in gas. And the dust is more or less primordial. It might have undergone some growth, but we think that the dust is just the dust that was left over from the formation of the star. On the other end of the spectrum, which is what I'm going to talk about today, are debris disks. And these are found around main sequence stars, so older, kind of more settled stars. They have, many of them have no detectable gas at all, and some of them have a significant amount of gas, which I'll talk about later on today. AU MIC, which I'm talking about today, falls into the category of no gas. And actually, along with the ALMA data, one of the sort of side benefits that we got is we got probably one of the lowest limits ever measured for the amount of gas in this debris disk, and it's very low, right? These are very sensitive observations, and we still don't see anything. Also, when we're talking about debris disks, we're not talking about dust that's left over from the formation of the star anymore. We're talking about sort of second-generation dust. So the idea is that in these systems, a planetary system has formed at least to some extent, and at least to the stage of forming Kuiper belt-like objects similar to Pluto. And the dust that we see in these systems, if you calculate the lifetime of a dust grain that's in orbit around one of these main sequence stars, and then you calculate the age of the star, the lifetime of the dust grain is very, very short compared to the age of the star. And so it can't have been there since the star formed. It has to be second generation. So what we're seeing is the result of collisions between these Kuiper belt-like objects, these planetesimals in this young system. And by looking at what's going on with the dust, sort of its dynamical properties, we can learn about the properties of the underlying planetary system. So that's what I'm talking about today. And of course, if you're interested in planets, you're really interested in this transition from protoplanetary to debris disks, because particularly if you're going to form planets like Jupiter and Saturn, you've got to do it before the gas disappears. So this is the paper that I read as a graduate student in my last year of grad school that really kind of set me off thinking about this idea. So when we think about the vertical structure of debris disks, this is kind of an old question, and people have been thinking about this for a long time. Most of the high-resolution observations of debris disks that exist historically have been taken at optical wavelengths, and that's because we had instruments like the Hubble Space Telescope that could do these very sensitive, very high angular resolutions and get a look at the really detailed structure. But this theory paper that came out by Philippe Thébault said, well, that's interesting, but the problem is that we cannot relate the vertical structure of debris disks measured at optical wavelengths to the amount of mass in the planetary system. And the reason for that is that when you're looking at optical wavelengths, you're looking at tiny dust grains, submicron to micron sized dust grains. And those dust grains are very strongly affected by the radiation field of the star. So the Thébault paper calculated a sort of natural scale height, and this depends on the mass of the star and the distance that you're looking from the star. So this was an example for the Beta Pictoris system, which is pictured down here. But there is this natural scale height that you expect purely from stellar radiation effects, where the stellar radiation exerts pressure on the dust particles. They get kind of blown out on these eccentric orbits. The eccentricity and inclination kind of work together to puff up the debris disk. So at optical wavelengths, these heights are very significant. And even at near-infrared wavelengths, depending on which system you're talking about and how far away from the star you're talking about. But when you get out to millimeter and centimeter wavelength observations, which is comparable to the size of the particles you're looking at. So when you start talking about millimeter to centimeter size particles, which is what you look at with radio telescopes, the natural scale height from radiation effects drops down to really nothing. So if you're looking out at millimeter centimeter wavelengths, you start to see, if you can measure this vertical height in the disk, you're starting to probe the underlying gravitational potential of the system. And in fact, in that case, as I'll show you on the next slide, you can show that the vertical structure is almost entirely determined by how much mass is hiding in the system. So the idea is that if you can measure the vertical structure at millimeter wavelengths, you're getting a fairly pure dynamical measurement of what is the total mass that's hiding in these systems. Because the only thing, debris disks are old, right? They have a lot of time for gravity to bring the dust grains down and settle them to the midplane. And so if they are stirred up, if they're puffed up significantly, that tells you that there's something stirring them, and that something must be the mass that's hidden in the system. And this is a really old question about debris disks, is we've always been able to estimate how much dust mass there is. That's pretty easy because we can see the dust. But what we haven't been able to measure or estimate is how much mass is hidden in larger bodies that's kind of hiding out in the debris disk that's too big for us to see with radio telescopes, but too small for us to see as planets. So, we can see like big Jupiter-sized things that are relatively close to the star, but we can't see a Uranus or a Neptune, especially if it's hidden in a dust disk. So the vertical structure at long wavelengths, this is a plot, again, from our ALMA proposal that's based on some work by Margaret Pan and Hilke Schlichting, who are two theorists who are currently working at MIT. Margaret is a postdoc there, and Hilke is an assistant professor there. And so they ran through the detailed physics of the collisional cascade and how exactly the collisional cascade works to dynamically stir up the objects in this debris disk. And so you can plot this relatively simple relationship between the scale height, the vertical puffiness of the disk that you measure at millimeter wavelengths, and the perturbing planet mass. Now note that I'm calling that a perturbing planet mass, but in their models you can't actually distinguish between, say, a single Neptune-sized thing and like a swarm of Plutos. So there's a degeneracy there, but you can get a total mass measurement for the system. So the scale height at millimeter wavelengths fairly directly measures the total mass of perturbing bodies in the disk. And there are two systems that we have been trying to do this on. AUMIC is the one that we now have data on. We're still waiting for beta-PIC data. Bill Dent is the PI of the beta-PIC program. I'm the PI of the AUMIC program. He's not interested in scale heights. I am. He's interested in something else, so I'm part of his project for that reason. And you can see that with the sub-millimeter array, we had enough angular resolution to, in theory, put interesting limits on the mass that's hiding in the debris disk. The problem was with the sub-millimeter array, we didn't have the sensitivity to take advantage of the resolution. So we had to use these really big blobby beams because the disks were just too faint and we didn't have the sensitivity to take advantage of it. So really what ALMA gives us is not only angular resolution. This isn't particularly impressive angular resolution, 1/10 of an arc second. I mean, it is for a radio telescope, but I shouldn't say that. With ALMA, we can actually get down to like this resolution ultimately at the high frequencies at the long baselines. But it doesn't take much to put really interesting limits. These are a few Earth mass limits on the total amount of stuff that's hiding in the debris disk. So with ALMA cycle 1, there's a little like factor of 2. I won't call it a fudge factor, but it's sort of a fudge factor because we're interested in the scale height. But since we get the top and bottom of the disk, we can actually do twice as well with the scale height because of the symmetry. So these are quarter arc second resolutions that give us basically 0.1 arc second measurements of the scale height that take us for AUMIC down to a mass sensitivity of just a couple of Earth masses. So again, this is the ALMA prediction from the proposal. If this one is for beta-PIC, I'm doing AUMIC, so you'll see the disk tilt in the next image, but that's just position angle stuff. So if the disk is puffy like this, it tells us this would mean that the vertical structure is similar to the scale height that was measured in the optical and near infrared. And that would tell us that there are really destructive velocities here. So it actually doesn't take a lot of mass to create the dust that we see in these debris disks. But it also tells us that there have to be large bodies that are stirring the disk. And if the disk looked like this instead, it would tell us that the velocities are relatively slow and erosive, and there's little stirring, so low mass in the disk. Okay, so, drum roll please. What do we actually see when we look with ALMA? I put in this proposal 3 years ago. I had to wait 3 years for the data. Here it is. Yay! Okay. So here's our ALMA data, and these results are highly preliminary. Like I said, the data just came to me via the internet about a week and a half ago. But if I take a simple elliptical Gaussian fit to one limb of the disk, and I've tried this for both limbs, and it's consistent for both limbs, I get a full width half max of 0.4 arc seconds for the minor axis. That's the puffy part right here. That's what we're interested in. And the beam is about 1/4 by 1/3 of an arc second. So if this result holds up under further scrutiny, which I can't promise that it will, but I'm hopeful that it will, it's pretty interesting because we can then come back to this plot. So we have to go about half of that. So 0.42 divided by 2 is about 0.2 something. And we come over here and we're measuring that the total mass is about 4 or 5 Earth masses in this debris disk. So that's this project. I'm really excited about it. It's been a long time coming. I've been waiting for it forever. But I think it's really promising as a way to finally probe the underlying mass reservoir that has been inaccessible to us in debris disks for a long time. So I'm happy to take questions. Thanks.
Is this disk perfectly edge-on?
It's a great question. So the limits from the scattered light observations are that it's within about a degree of completely edge-on. And so if you look at, okay, what's the radius in the disk that we're interested in? How wide is the disk out here? And with a sort of 1 degree uncertainty, we should not get a scale height this large from inclination effects alone. So great question. But that's something that we have to worry about in our modeling, but it doesn't look like it's going to be a problem for this data set. Oh, was there? Okay.
It's got a very asymmetric shape in optical wavelengths.
Yeah.
One side of the disk has been disturbed perhaps by a highline or
Okay.
some other perturbing. So is that going to have an effect if one side has been puffed up by some external?
It's a good question. So I'll have to take a look at that paper. It entirely depends on the nature of the thing that is disturbing the disk at optical wavelengths because, of course, some processes that cause disturbed morphology in debris disks are grain size independent and some are very grain size dependent. So it would make a big difference if it were a stellar flyby versus, say, some kind of ISM interaction or radiation pressure effect. And based on the ALMA data, so this is actually the second time that ALMA has observed AUMIC. It observed it at slightly lower, like a factor of 2 or 3 lower angular resolution. A beautiful paper by Meredith McGregor that you should all read if you haven't already. So that observation told us that for ALMA data, at least, the disk is highly symmetric. So it's very well reproduced by a symmetric ring. And just kind of looking at the preliminary data that we have here, it still looks symmetric, based on the stupid measuring that I've done of this image. So we might be able to have something to say in that conversation about what physical processes are causing the asymmetry at scattered light wavelengths.
For comparison, what's the dust mass?
What's the dust mass for AUMIC? I actually don't know off the top of my head. Oh, I see David here. Do you have that on the top of your head?
Roughly a lunar.
Yeah, okay. It's low. Yeah.
One more question. Which is the origin of the compact source?
That's a great question, too. So that's something that Meredith McGregor looked into the first time that ALMA observed this, because it was like, what is that? And in that paper, they investigate basically 2 scenarios. One possibility is that it was a compact asteroid belt that was unresolved in the original ALMA data. However, if that were the case, it should have been resolved in this data set, and you can see it still looks like a point source in this data set. The other possibility is and this is probably correct. It is most likely the chromospheric emission from this. This is an M star, so it's chromospheric emission from the M star. Yeah, it's about what 10? No, it's like 20-ish million years old, something like that. Yeah. So chromospheric emission from the M star, it's variable, it's ugly, it's terrible. This is something that I have to worry about a lot in this data set and take it out. But That's probably what it is.